Okay, good morning everyone. I hope you all had a good weekend, enjoyed the 1 extra hour you had to study, sleep, party, whatever. We ran out again of handouts down here. This is not, I don't think it's the reason we haven't printed enough. We've printed enough of all people who are enrolled in this course. So unless someone else decides to sit in this lecture because they think it's interesting, or whether there are some others have spare handouts. If you have a spare handout somewhere, please pass them back down. There are a couple of people in here who don't have. I see 1, 2, 3. We're getting close. Just thanks. Got one person here.
Thank you.
Who else needs a handout? You need one. Yeah. Anyone still without a handout? There's one. Okay. So that looks more right now. So let's get started now with the lecture. Thanks for passing the notes back down. Okay. Today we've got the center of mass as topic. Halfway through this lecture, the speed will pick up a little bit, and it should probably now getting more and more into territory which people haven't had yet, so please pay attention. The center of mass will be needed for the center of mass, which we'll also start talking about today. So, quick outline as usual, but that's more for you. So, there are, as I said the other day, there are an infinite number of frames of references we could choose, but there are a few special ones, and I've written them down here, which we're going to frequently use. One of them is the lab frame, so that's where we take the measurement. The other one is the center of mass frame. This is the center where the center of mass of the system is at rest and where there's total momentum of the system is 0. And we'll go through that. So for every inertial frame of reference, there exists a center of mass frame which we can make use of. It's very useful for many different kinds of applications, not only in classical mechanics, but also in relativistic cases, and that will be important when you start special relativity in the second half of Michaelmas. So more in that lecture. Now, internal forces and reduced mass, we'll start building up some of the components we need for the center of mass frame. So we have this diagram here on the right hand side. We've got somewhere an origin, two masses M1 and M2, and they have got internal forces. Could be electrostatics, could be gravity, whatever, but it's only internal forces where we can use Newton 3. So if we write those down, so we've got internal forces only. So F12 equals mr1 dot, double dot, sorry, should be acceleration, otherwise we are doing something wrong. And the other one, F21, the force on the second particle, is m2 r2 double dot. So this is what we have as basic. If I subtract both of them, I get r2 double dot minus r1 double dot equals f21 over m2 minus f12 over m1. Now, if we use the internal forces in Newton 3, we know that they're equal and opposite, equal in magnitude and opposite in direction. And if we define R equals R2 minus R1, we can of course do that game R dot equals R2 dot minus R1 dot, and hopefully it is clear then R double dot equals R2 double dot minus R1 double dot. So the acceleration we just differentiate with time one after the other. Probably should have also rewritten that as this is then what we define as internal force. This is the force the particles apply onto each other. And if we use this part and combine it and rewrite that equation a little bit, we get that the F internal equals, F internal times 1 over m1 plus 1 over m2. We just pull it out from this fraction, equals R double dot. And now the definition, define 1 over mu equals 1 over m1 plus 1 over m2. And we get F internal equals mu R double dot. So we have now here an equation of motion involving the internal forces and the relative acceleration R dot. That's the difference between both vectors, and the internal forces. So with respect, we've got the reduced mass, the relative acceleration, and the internal force. And mu can, of course, be rewritten as m1, m2 over m1 plus m2. This is what is the reduced mass. Of this system. This system, which in our case had two masses. Where we had two masses only. Now, the reduced mass is very, very useful in systems where masses can move around and shoot around. And we'll do one example to highlight its usefulness. And that's kind of the takeaway message. This defines the equation of motion, of the relative motion of the particles under internal forces only. So this one here. And you will see why. Now, building on that, we go to the center of mass frame. The center of mass is the point where a mass-weighted position vector or moments relative to the point sum to 0. The CM is the mean location of the distribution of masses in space. And that sounds very physical. A better way of visualizing is, it's another way, it's a point in space where you can suspend all those masses you have in the system, with the system not wanting to rotate or move more. So if you've got various dots around, you can suspend them there, and a weight here is counterbalanced by a weight elsewhere, so it's not moving at all, basically here with this one. If you would attach a string here and have some kind of rigid connection to those, that system would be stable and not rotate. Now, we have here a discrete system of point masses with respect to some origin, and n masses, and the center of mass of this system is defined as the sum from I to whatever n particles are, mi and then the difference of Ri minus where the position of center of mass is 0. So the, as it says, sum over I equals 1 to n, mi Ri minus Rcm equals 0. And if we solve this for Rcm, we get Rcm equals 1 over m times n equals 1 to n m I R I, where, well, the total mass m is of course the sum from I to n over all those little masses mi. So this is the definition. We're going to use it quite frequently to solve problems. Here we've got a discrete system, and from building on there, we can start solving some of the examples. Now, we've had the simple harmonic motion before in class. Before, one side was fixed, you had the spring, and you oscillated that around and determined the equation of motion there. Now we have two masses, m1 and m2, connected by a spring here, and you are asked to solve this. Sounds complicated? Well, I hope I can show you that it's actually straightforward if you set it up well, because this is where the center of mass really becomes very, very useful. Now, let's have a look at what we have in this problem. So as the graph shows, we have x as x2 minus x1. At x1 we've got the mass 1, and x2 we've got the mass 2. The L is the natural length of the spring. This is where the spring doesn't do anything, doesn't do any extension or contraction. Now from the slide before, equations of motion, because we only have internal force, is mu x double dot, although it's only, we'll do it in one dimension, that's why I can drop the vector notation, equals minus k and then x minus L x, that's it. So the internal force, this is from the before, we have only got internal forces, we can rewrite that with reduced mass times the acceleration, and that's the restoring force, or that's the internal force that comes from the spring. We have the difference to the natural length that gives us extraction and or expansion or contraction of the spring. And it always helps to have quick sanity checks in there in every step you do, and you can quickly check whether that's really the way we set it up as a restorative force or not. You would expect the spring is always trying to get back to its natural length, whether you compress it or expand it. So you have to check whether if x equals larger than L and x equals smaller than L, you get force smaller than 0 and the force larger than 0. So you have always this kind of forcing back to its original equation. And mu, well, I'll quickly write it down, mu equals m1, m2 over m1 plus m2. If we rewrite this equation here, we get x double dot plus k over mu x minus L equals naught. And that's the standard equation for a simple harmonic oscillator. When you see something like that, you know it will be an oscillation, will be one of the solutions. So this is simple harmonic motion. And from that, you know that the solution will look something like that. X equals x naught, so that's the overall amplitude, cos omega t plus phi plus L, where omega equals k over mu square root. So this is simply drops out from what potential solutions there are of the equation of the simple harmonic motion. Now, let's have a look how these things look like with respect to the center of mass. So, with respect to center of mass, so xcm, if I write it out according to the definition, m1x1 plus m2x2 over the big M, or big M is m1 plus m2, so the overall mass of the system. And then we have x1 prime, so the one with respect to the center of mass. So we do a quick transformation in the center of mass, equals mx1 minus m1 x1 minus m2 x2 over m. That's minus m2 x over m, capital M. And the same, x2 prime equal x2 minus xcm. This is from the definition of center of mass, which we've had before, in case you're wondering where that is coming from. Big M x2 minus m1 x1 minus m2 x2 over m, and that becomes m1 x over m. Those are symmetrical, and the reason for the minus sign is the way we've set it up, is that just the xcm is in the middle of both of them. Now, you can do a few sanity checks there as usual, and do a couple of simple examples. If you let one of the masses tend to infinity, for example, you get that same example as we had before, but we'll take just m1 equals m2 equals m, and then we have omega equals square root of 2k over m. So we got that extra factor of square root 2 because now both sides can move rather than just one side fixed of the spring and only one mass can move. And x1 prime equals minus 1/2 x and x2 prime equals plus 1/2 x. And that's not a surprise. We have symmetric masses, they have the spring between them, and they are always vibrating like this. So this is one example of where using the center of mass can be quite useful in determining the properties here, the simple harmonic motion of this spring example. So let's move a little bit on to a little bit more physical problems. Where's the center of mass of a continuous volume? Before we had origin, a couple of point masses dotted around, which is usually a very physicist approach, we assume the mass is all point-like. Now we have a volume there. So this is a little bit more challenging, but I think all the problems you will come across can be dissected and broken down into smaller parts. You just have to be careful to take the steps small enough that you're not running into any problems. Now, instead of those point masses, we have now a continuous distribution of masses. Say we've got a body like that, coordinate system. We want to find out where the center of mass is, and we have a density that is a function of r. So we've got the density rho is a function of r. So before we had the definition of the center of mass, sum from I equals 1 to n, mi ri minus rcm equals 0. So that was what we had before. Now this sum, if you go with small enough mass elements, becomes an integral, and we move out to a volume integral. So we start integrating over volume, density at point r minus rcm dv, we integrate over the volume, equals 0, where this dm equals rho r dv. So basically we moved from here to here by making these masses infinitesimally small, and at that element where that mass is, it has a density in a small volume, so that dm became r, the rho of r dv at that little volume element as it's drawn here. We go to this point r, at which we have a little point mass dm, and that dm equals rho dv. Density is given by the radius, and we've got a small little volume element. If we take this and solve it for RCM as before, we get RCM equals 1 over m integral v rho of r dv. And it's probably not surprising, well, this m equals total mass, and that's what you get, volume rho r dv. So if you just sum up, similar to the sum of all infinitesimal masses that there are, if we integrate up over the volume of all the density times the volume, we end up with the overall mass of the system. Now, we've been using vector notation now. Often you can break these problems down into symmetry and integrate via x, y, z, or radius, or whatever is offered in the example. And we'll do a quick example of one of those estimates for center of mass with a, well, you call it appropriate or inappropriate example. I don't know who's going to lift Mont Rainier at the center of mass, but it's a nice example. So as stated here, the Mount Rainier has approximately the shape of a cone. Assume uniform density, and its height is 4,400 meters. At what height is the center of mass? So in many problems, as I said, we can use symmetry. What are the two keywords to take away from this text? Any suggestions? Yeah. Bingo. Cone is one of them that describes a certain level of symmetry which we can use. And the other one is density is constant, so it's independent of position. And we can just pull it around in the integral as we want. Now, cylindrical symmetry, consider the y direction integrated from top to bottom. It's easier to do it this way than the other way around. You can try it putting the origin here and then integrating up. The result should be the same, but it's easier to start along this axis. So we start in terms of the y direction, and we only need to consider the y direction because the x direction in terms of symmetry, we know the center of mass can't be off that axis. This is what we can start with. Now, the center of mass in the y direction, in the somewhere along y equals, well, the volume integral rho of r dv over the volume of rho of r dv. We don't have the total mass, so we just write it out as it is. And since that's only a function of the y, we can rewrite that at y dm over 0 to h dm. Now, many of the problems you will have in physics will revolve around what is this dm. Now, this dm is the mass you have along a little bit of this dy here. We've got the cone, and it is basically the mass of this disk at a radius or at a position y that has a height dy and the corresponding radius of this cone at this particular y. So it is, we have got the surface area, which is r squared pi. We've got the density, and we have this little volume element dy at the position y. So we have a volume, and that gives us the little dm. So this is just, in other words, the mass of this little annulus around here as it's drawn. If you write that out, area times height times density gives you the mass. Now, r is a little bit of a useless or more complicated constant value here or variable here, which we need to reformulate somehow. So it's not a nice variable, but we can replace it with y. So the goal is to replace that with y, because that's our direction in which we integrate. So we had before that the tangent equals opposite to adjacent. And with that, we get the tangent theta equals r over y. And with that, we get r equals y tangent theta, which we can then use in this equation. And with that, we get ycm equals integral from 0 to h y rho pi y squared tangents squared theta dy over integral from 0 to h. Now just the integral over dm is rho pi y squared tangents squared theta dy. Most of the terms we can pull out and cancel. What we are left with is an integral from 0 to h over y cubed dy, integral from 0 to h, sorry for squeezing it in, y squared dy equals 3h to the 4 over 4h to the 3, and then we get 3h over 4 equals ycm. Now, there's still one point we have to be very careful about. So we started counting from the top. We are asked at which height is the center of mass. So we just have to be careful that the center of mass in the end is counted from the top. We reduce 3/4 of the height, so it's 1/4 of the height up. So the center of mass with respect to the bottom is actually 1,100 meters from below, and that also makes sense. You can imagine if it were up there, something would be wrong because of, well, most people probably have the intuition that this would not be the position where you can suspend the Mount Rainier from itself. Does anyone know where Mount Rainier is? Exactly, US state, Washington, the highest mountain there. And you can see the picture here. Not quite a cone, but physicists are often quite generous in terms of their assumptions. Now, we continue with the center of mass frame. But before I get there, the center of mass itself, there are a handful of standard bodies in physics. We had the cone, cube, sphere, disk, cylinder. Center of mass of those things, you should at least have practiced once or twice. I don't know what will be in the exam, but if you have these as your basic tools and you know how to calculate the center of mass of these things, it's a good exercise, and you may not be surprised if you come across one of those during an exam. Now, let's continue with the center of mass and go and have a look closer in the velocity and come up with one of the key properties of this center of mass frame. Now, I could continue using the integral notation, but the main thing is to grasp the concepts of the center of mass, the velocity, and the energy. So I'll use the summation convention for the point masses. I hope that you know how to transfer that. And the same applies, of course, to the integral. Now, going back, so the position of center of mass, we have this RCM equals 1 over m sum from I equals 1 to the n masses we are looking at, mi r I. Sorry. As it's shown there on the right-hand side for these point masses somewhere in space. And m, as before, m equals sum over I equals 1 to n mi. So velocity, we know, is the time derivative. So VCM equals RCM dot equals 1 over m sum from I equals 1 to n m I r I dot. Sorry, vector, should not forget the vector notation. I hope I have it everywhere. Yeah. So this gives us the velocity in the center of mass frame. And in the lab frame, the total momentum, P total, is given by P total equals the sum over mi Ri dot I equals 1 to n equals m v c m. So this is quite relevant, but hopefully not too surprising if you work it out from this formula here. Then this is basically what you have here. We've used down here to then, vector. And MIRI is M VCM. So the total momentum of a system in the lab frame that is comprised of n point masses is that to a single particle having the mass m, so the sum of those masses moving at velocity VCM. We're going to make use of that quite some time. Now, going from velocity and continuing with the momentum. So this is what I've written down, written before. VCM equals R dot Cm equals the sum and the velocity of a body in the center of mass frame. So we're going to transform now over from the lab frame to the center of mass frame. So I'm using, the dash notation. That's not a derivative with respect to any spatial coordinate, but just the velocity in the center of mass frame, Vi minus Vcm. So this is the velocity of particle I in center of mass frame. Now we can work out the total momentum of this system of particles. The answer is written already there, so what I should write down again hopefully will work out and convince you that this is really true. Now, if I do the sum over I of all the momenta in the center of mass frame, this is MIVI prime in the center of mass frame. I'm going to plug in the velocities with respect of the velocity of the center of mass frame. So this is basically rewritten at I MI VI minus VCM. So this is going to just going to plug that in here in the definition of the momentum in the center of mass frame. This is sum of MIVI minus, now going to use the definition here of the velocity of the center of mass frame, which we have up there. I just have to be careful with the summation notation. So it's the sum of I, Mi, and this term is another sum over j, Mj Vj over sum of j, Mj. So this one, if I sum up over all masses here, I get the total mass. If I sum up over all i's here, I get the total mass. They're gonna cancel, and I basically end up with sum over I, Mi, Vi minus sum over all j, Mj, Vj equals 0. And the index, whether it's I, J, A, or whatever you use, is secondary. You just have to stay consistent there and be very careful when you use those indices, that you use different indices where they are warranted and the same when you need to sum over those. So this is the case in a system with no external forces. This property is extremely valuable on solving many, many different problems, that the total momentum in a system like that is 0, and it's used from collisions to various other things, and we'll do some more collisions. Now, so far we've only considered internal forces. Let's have a look at the external forces. Now we have the force on a particle, mi on a particle I, mi r dot, double dot I equals F external, F internal. So this is just the internal forces and the external forces. Now, if we do the summation over all, it's important to notice that, well, we just do the sum of all here, sum over I. This is over all masses. We get all the external forces, the sum over all external forces, and the sum of all internal forces. This works out to 0. This is Newton 3, actio equals reactio, F12 equals minus F21, and you can generalize that to more forces. The example down here is shown for 2 masses, Mi and M1. So you can work it out here in terms of what's external forces and what internal forces. Now, from the definition of the center of mass, we have RCM equals sum over I Mi Ri over M, and RCM double dot equals sum over I Mi Ri double dot over M. Sorry, maybe I should have mentioned when I write sum over I mean sum from I equals 1 to n. This is just shorthand. So continuing from here, I get M RCM double dot equals F I M, sum over I Fi external. I just look in the equations up before, which I've had up here, and I plug it in such that we end up with this. So the motion of a system is equivalent to that of a single particle having a mass m acted on by the sum of all external forces. So the center of mass moves with a constant velocity if no external forces, that we've done before. But here now we have some kind of resulting external forces, this sum here, and if we work that out, we end up with this term as the equation of motion, because we have again some kind of force. The sum of all forces equals mass times the acceleration. So we're back to Newton. So in the last few minutes of this lecture, I would like to go the final step. Now we have to look into kinetic energy in the center of mass frame and in the reference frame and the lab frame. Now we compare those. Those are our two, as I said, most favorite frames: lab frame, center of mass frame. We've got one. This is our lab frame. And we've got some other frame which is moving with a velocity cm with respect, and that's our center of mass frame. As before, for any particle, the velocity in the center of mass frame, which I denote with this dash, equals the velocity in the lab frame minus the velocity of the center of mass frame itself. So if I rewrite that, Vi equals Vi dash center of mass frame velocity plus Vcm. These are the standard transformations back and forth. You can do that for position. You can do that for velocity. And as I said, this is the velocity of the particle I in the center of mass frame. Now, kinetic energy in the lab, T lab, equals 1/2 the sum over I mi vi squared. That's hopefully not a big surprise. Kinetic energy is 1/2 mv squared. We sum up all the kinetic energy of all the individual particles we have in this system. Now we're going to plug in what we have here. So we're going to plug that in there, and we end up with T lab equals 1/2 sum over I mi vi prime squared. So that's the velocity in center of mass frame. Then we get the sum over I mi prime vi dot vj dot not vj vi cm. That's a constant. This is where we're summing over, plus 1/2 sum over I mi vcm squared. So this one is the kinetic energy in the center of mass frame. So this is the velocity of all individual particles in the center of mass frame. If we sum this up, we get the kinetic energy of the system if we look in the center of mass reference frame. Now this, well, this is a constant. I sum up over the masses. I end up with 1/2 mvcm squared. So this is the kinetic energy of the center of mass with respect to the reference, the lab frame. Now, what about this middle term here? What about this? From the result, you probably can already guess what it will turn out to be. So I'll write it quickly out and illustrate what happens there. So we have mi vi prime dot vcm. Just gonna rewrite that a little bit so it becomes a little bit more apparent. I take the sum over mi vi prime over m times dot m vcm. I've just multiplied that by m over m. So that's those would cancel out, but I've done that to highlight that. What do we have here? This is the momentum in the center of mass frame, and that's 0 as before. So this is the 0 vector that comes out. So this is the 0 vector, and that times VCM, of course, turns out to be 0. Because the sum of all momenta in the center of mass frame is 0, one of the key properties. So what we arrive up here with is very, very useful, and we will use that several times in the rest of the course. And it can be used for collisions and tells us also that which energy of this center of mass frame actually is available for collisions to be going into, say, heat, sound, and can be wasted. So the lab or the center of mass frame or the lab frame always will contain this term there. So that's it for today. Tomorrow, I think tomorrow at 9 we continue with collisions, where we're going to apply that to a couple of examples, and hopefully I can illustrate how useful the center of mass frame is and its properties, and hopefully can describe what's happening in these systems and where you can apply them for. And with that, thank you very much, and I'll see you all tomorrow. There's one more handout in case someone needs one.